Okay, so are there any questions from the previous lecture? We just introduced graphs and we saw some basic terminology like degree, adjacency relationships, incidence, incidence of edges on vertices, and then we defined bipartite graphs and some other special graph classes, right? Like complete graphs, cycles, and so on. So are there any questions here? Okay, if not, then let's move on to understanding this question that Euler had posed. We had seen this. We had just seen the question last time. So whether there exists, so you're given a set of roads or bridges, and you want to ask this question: can you travel from one place to another place by visiting each of by walking across each of these bridges exactly once? So that's the question we want to ask. So given any such drawing of the city, can you decide this question? Can you say yes or no, depending on the drawing that is given? So to understand this, to try and solve this question, we need some more terminology. So let's see that first. So we did end with paths, right? So we saw what paths are. So let me just refresh that. So we're given a graph G. So what is a graph? It's described by two sets. One, the set of vertices, and E, the set of edges. And E is the set of edges. And vertices are usually finite. So you have like V1, V2, so on up to Vn vertices. And you have edges. So an edge is actually a pair of vertices. So in undirected graphs, this is an unordered pair of vertices. So you can use curly braces to denote the edge. Whereas in a directed graph, it's an ordered pair. So this means that there is an edge from the vertex U to the vertex, right? And a directed graph is called a diagram, in short. And what is a path in a graph? So a path in a graph is just a sequence of vertices. So if you think about a graph given to you like this, yeah, I'm just trying something. So let's say you have this graph, and you want to ask for a path U, V, W, X, Y, Z. So a path from U to V is just this edge, right? There's also another path from U to V, which is U, B, V. There's another path from U to V, which is U, V, U, Y, Z, A, B. B. Another path is U, B, A, X, W, B, and so on. So there are several paths on the same graph from one vertex to another vertex. And usually a path, you can think about it as a sequence of edges. Exactly the way in which the pointer moved, right? So from U to V, the edge UY, YZ, ZB, BB, and so on. But whenever you think about a simple graph, there's going to be exactly one edge between any pair of vertices. So that is why a path is usually described by a sequence of vertices in the case of a simple graph. And we will most likely deal with simple graphs. So for us, whenever we say a path in a graph, it's a sequence of vertices. Right? So let's call this V0, V1, V2, so on to Vn. Right? Such that V0, V1 is an edge in the graph, V1, V2 is an edge, and so on. Vn minus 1, Vn is an edge in the graph. Right? This is a path from V0 to Vn. And usually, whenever we talk about paths, right, we want every vertex to be a distinct vertex. Right? So, for example, to go from U to V, right, I can do this, U to Y, then Y to U, then U to B, and B to B. Right? I can actually walk across the edge UY twice. It makes sense, but we don't call that a path. So whenever someone asks you to describe a path, it's a sequence of vertices where every vertex is distinct. You can think about it as you have to walk across that edge only once. Okay? Whereas if you're allowed to walk across an edge multiple times, that's usually called a walk. We won't use this in this course, but you might see this in some textbooks. So walk is also a path, but now the edges need not be distinct. Like you can walk across, just like you take a walk, right, on the road, you can cross the same road several times. But a path is a sequence of distinct vertices. And another terminology that is used is the term trail. So a trail is also a sequence of vertices, but every edge should be distinct. So here, if you look at this particular sequence, right, path here, the every vertex is distinct and every edge is distinct in the sense that uy and yu, right? You cannot walk across twice, like you have to walk only once. Whereas in a trail, every edge is distinct. So I'll just give an example of it. So trail is one edge, every edge is distinct. So what do I mean by that? Let's just take this graph. Let's see. So if you look at a path from V to Z, you have this path V, W, X, Y, Z. This one. Oh, I missed image. So V, W, X, Y, Z. That's a path from V to W to Z. So what is a trail from V to Z? This one. V, X, W, Y, X, Z. Right? So what is that? You have V, you go to X, then you come to W, you come to Y, you go to X, and you go to Z. So every edge is distinct, but you can enter and leave a vertex you can enter a vertex from one vertex, from one edge to one edge and leave a vertex through the other edge, the same vertex. So X is repeated twice, right? But the edges are distinct. You came in through B and you went out through Z. So that's okay. So that's called a trail. Okay, so this is like you have interconnecting roads. You come to a junction and then you can take any of the like diverse paths that are given to you. Okay. So is this clear? This terminology, what is a path and what is a trail? In path, the edges are distinct, the vertices are also distinct. In trail, vertices can repeat, but edges have to be distinct. So in some sense, the question that Euler had posed, we were seeing, asks you if there is a trail, right? Because you can enter a bridge and you can leave a bridge. You should not cross the same bridge twice. We will recall the problem anyway, but is the terminology clear? Path versus trail. Okay, so I must mention that depending on the books you read, there will be several other new terminologies that you'll come across. So I must caution you that there are things like walks, closed walks, trails, paths, so many such terminology are there, simple paths, and so on. So whichever textbook you follow, just ensure that it is consistent. Whatever is the terminology used in that textbook, you have to be sure about it. Because some people interchange this terminology, I'm not very sure. But path and trail are usually very standard. But other things like, for example, walk. Also, some books, they prefer to use a sequence of edges for paths. Like what they do is they write this as E1, this is E2, this is E3. And if someone asks you to describe a path from U to X, they will say E1, E2, E3 is a path from U to X. But yeah, we will probably use the vertex labelings only. First of all, I don't want to confuse by introducing edge labelings. And secondly, most of the graphs are simple. So we don't have to care what is the edge. There's only exactly one edge between U and P. So let's just use the vertex labels. Okay. Is this clear? Or if there are any questions, you should ask because there will be more stuff. Okay. So then let's move to some more terminology. So what is a closed trail? It's whatever you would expect it to be. So it's a path where every edge is distinct and you begin and end at the same vertex. So the trail is closed. So initial vertex is equal to final vertex. Okay. For example, a closed trail from V to V is like V, X, Z, Y, V. Every edge is distinct. Or if you want to like repeat vertices, you can try V, X, Y, Z, X, W, V. Clear? What a closed trail is? Okay. So now we have some idea, right? What paths are, what trails are. So now let's say we are given a graph like this. Just drawing some arbitrary graph. So this is a graph, some sort of a road network, let's say. So what do we mean by saying that this graph is connected? In a road network, what would you mean, like if you have like 10 cities and you mean that these 10 cities are connected by a road network? A map is given to you, right? What would you expect it to be?
There is a path from one node, any node to any other node.
Exactly, right? That should be a way to connect every city to every other city. So you say a graph G is connected if there exists a path from U to B for every pair of vertices. UB. Such a graph is said to be connected. And you must remember that so far we are dealing only with undirected graphs. So things can get complicated when directions come. Right? So like for example, there might be a road from Chennai to Mumbai, but there may not be a road from Mumbai to Chennai. So such things are possible. But in undirected graph, you say it is connected. So I must write an undirected graph. See, is connected if there exists a path from U to B for every pair of vertices. Right? Is this clear? So this graph is connected, the graph on the right hand side. So now is this graph connected? This whole graph. Let's call just this whole is one graph, which is an undirected graph. Right? Is this graph connected?
No.
No, right? Because there are a pair of vertices UV such that there is no path from U to B. So what are these individual things then? But you still have two things. This portion is connected and this portion is connected. It's just that across these vertices, there are no paths. Right? So these two entities here, like this object here and this object here, they are called connected components. Right? So what is a connected component? It's a portion of this graph within which everything is connected. Right? But these two entities individually are disconnected. So usually we call them like C1, C2. Right? C1 and C2 are connected components of the graph. So, okay, just to write down the formal definition of connected components, let me just talk about subgraphs. So this is a graph, right? This whole thing is a graph. In fact, even this is a graph. So now if you look at only these edges, right, whatever I've given in red, that is called a subgraph. So there is a graph G. The vertex set of the graph G is, let's say, E. Now you can define a subgraph H which has vertex set W, where W is a subset of V and F is a subset of V. And this H is called a subgraph H. Okay. So for example, this thing in red, right? Whatever I've written, this is a subgraph of the graph. Just an edge is a subgraph of the graph. In fact, this whole thing is a subgraph of G. So now can somebody define connected components of a graph in terms of subgraphs? What is a connected component?
Subgraphs, which each subgraph is connected, but altogether they are connected.
Altogether they are not connected, right? Okay.
Mutually disconnected.
Right. So you can write this as a connected subgraph. So every connected component of G is a connected subgraph. G. So now let's just look at what he had suggested and look at the definition. So let's look at this alone, right? The one in red. So this one, and let's look at this one. So are these two connected components? Can we say that? So, so in some sense, if you paste these together, it is connected, right? So they are not connected components. So what do I want to say? So this is you say a connected component. This particular component is a connected component of the graph. If it's a connected subgraph of G, right, and it should not sit inside any other connected component, right? Is that correct? Like you cannot say that this portion is a connected component of G. No, you have to make it as big as possible. Otherwise, you can just put every edge in one connected component. It doesn't make sense to define it that way. So you say a component is a connected component of G. It's a connected subgraph. And oops, sorry. And it is not proper subgraph.
Excuse me, ma'am.
I will just
Aren't-
complete this sentence 1 second, so that maybe the doubt is about this. So this proper have to define. Yeah. Let me. What is the question?
I mean, aren't there any more conditions on F? Because if we
Any more conditions on? Actually, I couldn't hear. Is it only me?
any more conditions on W and F, or am I audible?
Yes, yes. You mean in the definition of subgraph or in the definition of connected component? Where are
No,
where is the
I mean in the definition of subgraphs.
Uh-huh.
Is this the complete definition, or are there?
So
some
why
more
do you think that it is not complete?
Because ma'am, if we take W, this and we could
Sorry,
take some
I could not
other
hear. Why? Okay, is everybody else able to hear clearly? Shubham, can you just repeat the question?
His voice is cutting for me as well.
Okay. Can you repeat the question or can you try to type? We'll wait.
Am I audible now?
Yes, yeah.
I was saying that I was thinking this might not be complete definition, because like we could take some vertices and then some other edges which are not part of these vertices, which are not between these vertices.
Right. So you mean that you can pick these two vertices and then a few edges, right? Here.
Yes, ma'am.
Right? Yeah. So generally when we talk about subgraphs, we mean that the vertex set should be a subset of the original vertex set of the graph, and the set of edges should be a subset of the original graph. But what you're thinking is sort of right? So what she's saying is, I mean, you can just pick some arbitrary set of vertices and edges, and you don't care, like it will be like few hanging vertices and few hanging edges, right? Doesn't make sense. So what she feels is incomplete is actually sort of correct, but I'll have to do some more introduction, some more definition of that, but I'll do it anyway. Okay? So what she's saying is some vertices are there and some other edges are there. So what one would expect is h is equal to W comma F, where W is a subset of B and F, right, contains edges only on vertices in W that are in G, right? So what do I mean by that? So you pick a subset of vertices, and you can also choose to pick a set of edges, but edges from the graph. But the endpoints of both the edges that you pick must actually be in the vertex set, so that there is no this dangling around vertices, right? That's what you would expect the definition to be. In other words, H is W comma F, such that for all A comma B in W, A B is in the set F. Does this convince you that it's a reasonable definition? H has the same set of edges as G, but only between the vertices in W. right? So this is called an induced subgraph. Right? So H is said to be an induced subgraph. So in other words, just a couple of isolated vertices are a subgraph. There is a couple of isolated vertices. If there is an edge between them in the original graph, that's not an induced subgraph. Is that clear to everybody? Actually, we will not use induced subgraph that much in the course. I did not introduce additional terminology. So this connected component, is it clear? It's in some sense maximal, right? So within this connected portion, you cannot put two components. This should be like clear. So you might be given a graph and be asked how many connected components are there in the graph. So you should be able to count. So here there are two. So if I add one more set here, just a minute, and add this to 3, there will be like 3 connected components. One is this, the other is this. Okay, any questions so far? If there are no questions, then I'm going to throw like more definitions. Is this clear? Connected components? But you must remember that we have defined connectedness and connected components only for undirected graphs so far. Okay, maybe let me just take some more time and define this for directed graphs. So what would you expect the definition of connectedness to be in a directed graph? When do you think we should say a directed graph G is connected?
I guess we would want a path, like we still would want paths between any 2 points, but the paths need to be like directed paths.
Right. So let's just formalize what he's saying. So suppose you're given a digraph like this, some directions like this, just arbitrarily orienting edges. So you say that this graph here, what he means is that you should say that a directed graph G is connected whenever there exists a directed path from U to V and VT. Right? So both ways you should be able to do. Right? So that is what it is. So you say a directed graph is connected, but with some minor changes. I'll introduce that. Connected if there exists a directed path from U to V and from VT. Right? And we call this strongly connected because in some sense you have a path from both U to V and from VT. You can go like two-way. So such a graph is said to be strongly connected. So now you must be able to guess, right? What do you think it is weakly connected?
V to U or U to V.
Right. So either there is a path from V to U or there is a path from V to or U to. Right? So another way of saying this is look at the graph, forget the directions. Just look at the graph as an undirected graph. And if that graph is connected, then it is called a weakly connected diagram. Is that convincing? Whatever he said is exactly the same thing that I said. U to V or V to U just means that you forget the directions in the graph, treat the graph as this undirected graph and see where it is connected or not. Right? So you say the directed graph is weakly connected if the underlying undirected graph disconnected. So what do we mean by underlying undirected graph? Given a directed graph, just forget the directions. Is this clear? Similarly, we'll have the notion of components also, but now you'll have like strongly connected components and weakly connected components. So some components, for example, in this component, maybe there might be a path from U to V and V to U for every U. Whereas in this graph, probably there is not. For example, it might be something like this. Right? So this component is weakly connected. Whereas if I add all possible, add right directions, then this component will be strongly connected. Is it clear what connectivity means in directed and undirected graphs? So if there are any questions here, we'll take them. Then we'll move to solving Euler's problem.
For a simple directed graph, like if we have does complete
Sorry?
complete strongly connected directed graph exists?
That is, you have an edge, we have a path from U to V and V to U. Can there exist complete?
Yes, complete.
Yes. Yeah, there are, and we will see one example. Probably by the end of this lecture, if time permits, otherwise it's.
Won't there be any bound on the degree of each vertices to exist, to have such strongly connected directed graphs? Simple.
What do you mean by bound? Lower bound, is it?
No, upper bound. Like there might be so that, or will it, like weakly connected graph will always exist. Every complete graph is weakly connected, but strongly connectedness, and which is simple, that is, there shouldn't be any loops. I mean, yes, between two distinct vertices should have only one edge, which is directed, and shouldn't there be any upper bound on the vertex degree in each of the vertices of the graph for strongly connected?
There could be just one edge, but there can be paths, right?
Yes.
Because here, when we say strongly connected, we don't say that there should be an edge from U to V and V to U. Then it becomes messy. We're only saying that there should be a path from U to V and V to U. Right?
Okay.
Right? So it can be that you have an edge from U to V, and in the other direction, you have a path from U to U. You get the point, right? That is possible. If it had been an edge, then whatever you had you say would work. I mean, simple graphs, it's not possible, right? Unless you take multiple edges. Okay.
Ma'am, I had a question. Ma'am, like in a weakly connected graph, like what will a strongly connected component look like?
So, so you have a weakly connected digraph. So when I mean by, what do we mean by weakly connected digraph, right? So something like this. So this is one weakly connected component. Right? But there can be another strongly connected component here. Right? So these two together. So what is this graph? This graph as a whole is weakly connected. It has one weakly connected component and one strongly connected component. But the underlying undirected graph is, So what should I do? I should make this graph. Yeah, I will just put some direction. So the underlying undirected graph is connected. But when you look at the component, right, it might be that you won't be able to see weakly. All the components will not be weakly connected. That is why you have this weakly and strongly connected components. Yeah, but for this lecture, at least for this course, you will use only connected components and undirected graphs. But it's good to know that these things like exist. In case you want to like solve the directed versions of the theorems that we see. Okay, so let's move on to, I hope there are no more questions. Let me just move to Euler's. Okay. So what was the question that we saw last time? There are some land masses and there are some bridges, and you have to walk across every bridge exactly once. And if you look at the bridges of Königsberg, I don't know if you remember, but this was the structure. All right. So there are like 4 vertices and there are 7 bridges. Now the question is, can you begin from any one of these vertices, traverse every bridge exactly once? So bridge is an edge now. So traverse every edge exactly once and return back to the place where you started. You can start at any of these 4 vertices. There's no condition there. Is it possible? Did you try? So what are we asking? Does there exist a closed trail? So a trail, if you remember, every edge must appear like only once, right? There is no repetition of edges. So does there exist a closed trail that includes every edge? That is the question. And such a closed trail that includes every edge of G is called an Eulerian trail. So did any of you get to try? Does there exist? Maybe you
It's
can.
not possible.
Why do you think it is not possible?
Ma'am, there are 3 vertices which have odd number of edges connected to them. So, I mean, if you think of a trail as entering a landmass and exiting a landmass, then there are 3 different landmasses where we have to enter, exit, and then enter again, or either start from that landmass, exit, enter, and exit. But we can start from only one landmass. So there'll be 2 other landmasses where we have to finish. So that's a contradiction.
Right. So what he's saying is you can like enter and leave one. You can use one edge to enter and one edge to leave, but then there will be hanging around edges which you cannot cover because some of the vertices have odd. At least in this graph, that seems the reason why this such a trail does not exist, right? So let's look at some more graphs. So does this have? I'm just drawing these 3. So like figure out if these have. So let's call this G1, G2, G3. So does this have?
Yes.
This one, right? Does this have? It might take some time, right? You have to like sit and work out, like try from every possible vertex, try every edge, get hit.
No, ma'am.
Okay, so some of you see that it seems unlikely because this also had some odd vertex degree here. This also has. So his argument sort of seems to work out. Okay, but here, suppose this is A, let's say, and let us say this is B. Okay? I don't want you to, okay, okay. So now maybe you don't have to come back to A. Maybe you could end at B. Right? Then is it possible?
Yes.
So can you tell us what is the?
I can directly go from A to B.
No, you should cover every edge in the graph, right?
Oh, you can start from A to the middle element to the top
Okay,
right
let
element.
me just put ABC to facilitate.
A, E, C, D, B.
You have not covered these edges, right? So what
It's
is
not
an
possible.
Eulerian trail? This is something you must remember, that it's not a path from A to B, right? It's a path where you should visit every edge. So you must remember of this postman who wants to actually visit all the places. It's just that he should not walk across the same edge twice. Is that clear? Yeah, so I think the definition is unclear. So you say a graph has an Eulerian trail or a graph is Eulerian. Let me write that down. G is Eulerian. If there exists a closed trail that includes every edge of G. Right? Is this definition? This should be like super clear. Like no doubts there. I see some of you giving me paths from A to B. That's not what we want. We want to like cover every edge from A to B. Right? If you do this, then this edge is missed, and so on. So maybe I will just delete this. Okay, this one. So if you look at A, B, this graph, so initially whatever argument we had said, right? If you look at it closely and try to see all possible possibilities, you cannot start at any vertex and end at the same vertex and cover all the edges. But if I ask you to produce the same trail, but you can start at A and end at C, then can you do that?
Yes.
So can you give the order, like the path?
A, C, D, A, B, C.
Right. So he has visited all the edges. He started at A and ended at C. Right? So now this is called an Eulerian path. It's not closed. So this is closed. A, G. Moves every edge of G. So is the definition clear? If it's not clear, we can go over it again. Yeah, so what is, so just to ensure that you have understood the definition. What is an Eulerian trail in G1? Just trying to see.
A, B, C, D.
This one, or you can even start at B and D. And if I ask you to start at C and then at A, you should not say CA. No, that then these edges are all uncovered, right? So it should be CBA, CDA, or anything else. Maybe CDA, BA, ACBA. That's also fine. Right? So this is clear. The definition. Okay. So now the question is, okay, in this graph, somehow you probably like sat through the day and worked out and figured out, okay, I should start here and then I go here, I get stuck. So this graph G is not Eulerian. This is probably because you tried to like draw the diagram without lifting the pencil. But in general, if you're given a graph, is there a way to figure out whether the graph is Eulerian or not? Just from the experience you've learned here, do you feel that it has something to do with the degree or the path? What should it be?
If
Or
all
the
degrees
edges?
are odd, it will work.
All degrees are odd, what will work? You will always
Even,
have
sorry, even. My bad.
No, it can have at more. Right. If all degrees are even, there will be a trail.
right? You have a
If and
feeling
only
that
if.
because you can enter via one and leave via the other, right? Always. So let's try to see if that is true, whatever he is saying. But for that, I need one. It's small lemma. So let me just prove that first. It's not a big, it's not even worth a lemma, but I'm going to write it down. So let's say that G is a simple graph. And the degree of every vertex is at least 2. Then G contains a cycle. So let's separate this. So we have a simple graph, and every vertex we know has degree at least 2. It could probably have more. And I want to say that it has at least this some cycle in G. Okay. So let's start at some vertex. We know that it has degree at least 2, right? So you can always pick one vertex that is adjacent to V, that is not the one preceding it. So for example, this is V, V1, V2, let's say. Right? So you begin at V, you go to V1. Because this had degree 2 and you went to V1 via V, this path you exhausted. Now there's another edge that is remaining that you can go out via. You pick that edge and you keep doing this. Right? And you will definitely, because the degree is 2, you will definitely get back to one of these vertices again. And at some point, you will come back to V because each vertex has degree at least 2. Is that clear? I'm just going to start at V and construct this. Is this clear? So if the degree of every vertex is at least 2 in a simple graph, then definitely there must be a cycle. Okay. So now let us.
Ma'am, but we can't necessarily start with any point, right? Because there might be some points where the graph intersects itself later, but it doesn't cycle back to the original point.
Yeah, you can start anywhere. Let's say you start at V only. You can go cycle around and you will probably reach D1, not V. At that point, you just cut off, remove this and say that this is the cycle. Did you get the point? Was it unclear? Like you can start anywhere, but you may not get back to V itself. But you will definitely get back to one of the vertices that you have visited earlier.
Yes, ma'am. Okay.
Yeah, I'm not saying that it's a cycle from V to V. If you contain a cycle, that's what I'm saying.
Ma'am, could you explain the reason once again?
Okay, so you know that every vertex has degree at least 2, right? It's a simple graph. So let's pick one vertex, some arbitrary vertex. You have like n vertices, pick one vertex, this one, right? And now this is the first vertex. You know it has degree at least 2, so you can choose one of its adjacent, adjacent vertices, right? Either you can choose V1 or you can choose V. Let's say you choose V1. Now V1 has degree at least 2. In the worst case, it will have degree exactly 2. Even in that case, you'll have at least one more edge to go out via. You need not choose the same edge via which you came inside V1. There's no notion inside here because the graph's inverted, but still, you use this edge to come into V1. You can use another edge to go out of V1. So this way, for every vertex, you can come inside via one vertex and go out via the other vertex. And keep doing this. Because there are only n vertices, right? At some point, you have to return to one of the vertices that you earlier visited, because at every place you have a choice. The degree is at least 2. Right?
Yes, ma'am.
So there must be a cycle. But what he said was it may not end at V itself. That is true. Like for example, you may come here, go to V1, do this, and come back to V1. Or you might just come back to V2 itself. But I'm just saying that there is one cycle. It does not have to start and end at V. For example, this is also a cycle, right? Maybe you do this, start at V, go to V1, go to V3, V2, and choose this, you'll come back to V1. In which case you say that, okay, the cycle is this one. Just discard the V1. Okay. So now this is the theorem of Euler. So first you must remember that if the graph is disconnected, it is not Eulerian. Right? Because there is no edge, there is one isolated vertex. It doesn't make sense. So we will write if every vertex is evenly. Okay. So let us try to prove this. Whatever comments you made earlier, we are just going to formalize. That's all. So first, the easier connection. Suppose the given graph is Eulerian. Then you know that there is a path, a closed trail that begins at one vertex and ends at the same vertex and visits every edge in G. Is that clear? So there is an Eulerian trail. Let's call this trail P. G. Eulerian trail. Which means that it's like a sequence of vertices. V1, V2, V3, V4. And it will end at V1. And every edge in G is in this tree. Right? So what do you know? So this vertex V2, if you look at it, the contribution of this Eulerian path, the degree contribution to this vertex is 2. Right? There is V1, V2, and there is V2, V3. At V3, there is V2, V3, and there is V3, V4, and so on. But you must remember that in an Eulerian trail, the same vertex V2 can repeat several times. Right? Like just we saw here. For example, this one. Right? You can go and come via the same vertex again. So V2 might appear several times in this trail. But every time it appears, the degree contribution will be 2. And every edge appears exactly once in the trail. Right? It's not repeated again. Which means that the degree of every vertex will be a sum of certain number of 2's. Like if V2 appears k times, V2, 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 and so on, then its degree will be 2k. So the degree of V is a sum. So k 2's, which means that this is. Is this clear? It's because every edge occurs only once. So this direction is fine. So if the graph is Eulerian, then every vertex is within the. Now the harder direction. Suppose you have a graph G where every vertex is even.
Eulerian trail, as in closed Eulerian trail.
Sorry?
Closed Eulerian trail. This theorem is characterizing for that. If you scroll up that square with one diagonal connected has an Eulerian path which is not closed, and it does not have all the event vertices. ABC, that G3.
This one you're saying?
Yes.
Uh-huh.
This does not have every vertex with degree 2, and there exists a non-closed Eulerian trail.
Yeah. So I just said that the graph is Eulerian, which means that it has an Eulerian, closed Eulerian trail. G is Eulerian if there is a closed.
Oh, okay.
Yeah. So I will write this. Or let's write a connected graph has an Eulerian tool, closed trail. Yeah, there are too many terms, I understand. We still haven't seen the characterization for this case, right? Where you can start at A and end at C, but not go back to A itself. That also has a characterization, we'll see that. But right now, we are only looking at the closed Eulerian trail condition. Any questions on what we are doing so far? No questions? Yeah, there are questions, please ask. There are too many terminologies, I understand.
Now could you do the proof once again?
Sorry, this one, the one that we just saw?
Yes.
This one? Okay. Okay. So now what are we trying to show? You are given a connected graph and you are asking, does there exist a circuit, right? You start at a vertex, end at the same vertex, and visit every edge exactly once. Does there exist such a two or not? And the statement tells us that if every vertex in the graph, in the given graph, has even degree, then such a two exists, right? And only then such a two exists. So the one direction of this is, suppose the graph is Eulerian, then you have to show that every vertex in the graph has even degree. Right? So we know that the graph is Eulerian. What does it mean? You have a closed circuit where you start, for example, this is the one. You start at A and get back to A and visit every edge, walk on every edge exactly once. So there is such a path. So let's write down the path. Right? It has V1, V2, so on, to some vertices, and then it will cycle back to V1. Right? But you must remember that any vertex can appear any number of times. Is this clear? Because you can enter via one vertex and leave via the same vertex. For example, yeah, this one, right? There was this example. So that's what a trail is, right? It's V, X, W, sorry. V, X, W, Y, X, Z, and so on. So in this trail, X appears twice. So a vertex can appear any number of times. It's just that an edge appears only once. Okay? So V2 appears, let's say, some K times. So what is the degree of V2? That is what we're trying to see. So in this path, if you look at it, you enter V2 from V1. Right? So which means that this sort of a thing is there in the graph. V1, there is V2. And V2, there is an edge from V2 to V3. That's why the Eulerian tour took that edge out. Now, although V2 might appear again in this list, these two edges will never appear again because this path P is Eulerian. Right? It will visit every edge exactly once. So whatever edge you accounted for in this degree, you will not recount it. So there is no counting mistake there. So this and this is done. If at all V2 appears again, there will be one more edge. Let's say it will be V4. So from V3, you'll go to V4 and then you will enter V2 again via V4. And then you'll probably get out of V2. Is that clear? And every time you list V1 here in this list, the degree contribution will be 2. And there is no repetition, no repeated edges. So V2 appears K times. The degree of V2 will be 2K. And this is true for every vertex in the graph. So every vertex is even degree. Is this clear? I mean, we can repeat this again if you have doubts. Because it's the first time we're seeing graph theoretic arguments. Right? So it takes
Ma'am, by closed trail, you always mean that every edge is covered exactly once, right?
A closed Eulerian trail. So generally, if you talk about a closed trail, that is not necessary.
Oh, okay,
So,
but for
so then-
Eulerian trail, that has to
Yes.
be exactly once. Okay.
So Eulerian trail, you can immediately remember that this bridge problem is there, and that is what Euler is trying to solve. So for that, you want a closed trail that visits every edge exactly once. But if somebody just asked you to give a closed trail, then you don't have to like cover every edge. Is that clear? Yeah, there are a
So,
lot of
ma'am, being
terminologies.
Eulerian implies that it has such a Eulerian closed trail, right?
Yes, you say
okay.
that a graph is Eulerian if there exists a closed trail, which means there is a sequence of vertices that starts at one vertex and ends at the same vertex and visits every edge exactly once.
Okay.
Now it's clear, right? So one direction should be clear. Yeah, if there are questions, like, please ask. Okay, so now we have the other directions. This is this direction. So in this direction, it's assuming that every vertex has even degree. Right, now we want to construct an Eulerian tour. So what do we need to construct? We have to begin at some vertex, end at the same vertex, and visit every edge exactly once. We have to set up such a path. It's such a closed path. And the proof, so this is the hard part of the proof, which Euler showed. So this is by induction on the number of edges. Okay, so now if there's only like one edge, if every vertex is even degree, and the number of edges, it cannot be just one, right? That's not possible. Otherwise, then the degree will be one. So you can consider n equal to 280. In this case, there is definitely an Eulerian trail. So base case is like simple. Not going to the base case. Now suppose the graph is connected. We are only dealing with connected graphs. So let's say G is connected and every vertex has degree 2. So what do we know in this case? We just showed some property of G whenever every vertex has degree at least 2. Nobody recalls?
It contains a cycle.
Right. So we showed that G contains a cycle. Right? Graph is connected. This implies that G has a cycle. Let's call that cycle C. Right? Now, it might be that C, the cycle, contains every edge in G. If C contains every edge of G, then what can you say?
And then that is the Eulerian closed trail.
Right. So then done. Is that clear? So we know that the only case we have to handle is when cycle does not contain some edges of G. So it's something like this. Just draw a picture. There are some more pieces here. Okay, so let's say this is the graph G and this is the cycle C. We draw the cycle in a different way. This is the cycle C. But this whole thing is the graph. Okay. Now I want to get to the induction hypothesis. So in the inductive hypothesis, I assume that whenever the graph has, let's say, n minus, not n minus 1, let's say m minus 1 edges and every vertex is even degree, there is a closed Eulerian trail. That is the inductive hypothesis. Okay. So now what do you think? I'm given a graph G and I want to prove by induction on the number of edges. Let's say there are m edges. Now I want to get to the inductive hypothesis. So what should I do?
I think we can remove the cycle sort of, because we start at one point and we go through the cycle and we get back at that point and we have essentially a graph with fewer edges.
Right. So what he's saying is this cycle we anyway know is Eulerian in some sense, right? So if you just look at the cycle, it is Eulerian because it starts at a vertex, visits every edge and returns back to the vertex. Just that there are some other dangling portions here that you have to cover. But these we know have fewer edges than the original graph because after we remove the cycle, so then we can use inductive hypothesis. That is what we are going to do. So what we are going to do is consider the graph G after removing the cycle. Edges in C. So what does that mean? Let me just oops. So now let me just delete the cycle. So then these edges, vertices will still be there, but just the edges will be deleted. Right, so this is the graph G minus the edge set of the cycle. Okay. So now this this graph we know has should this graph be always connected?
No.
Not necessary, right? So let me call this graph H. So H may be disconnected. So the moment it is disconnected, what should you do to deal with the independent portions? What are these? These small ones.
Connected components.
Yes, connected components, right? Okay, so I will just, I think I drew the picture sort of incorrectly. Let me just say this was the original graph. because otherwise this vertex does not have even degree, right? So then the drawing was incorrect. So I will just delete all this one. So H might be disconnected and it can have several connected components like this. But if you look at each of these connected components, they will have fewer edges, right? So every connected component has fewer edges. Is this clear? Right? So you have to use the inductive hypothesis. Now can someone try to like finish the argument?
Ma'am, can I say the argument?
Yeah, you can try.
So the connected, like before removing the cycle, you would have the now connected component connected to the cycle at a particular edge. So you start at an edge and find another cycle inside the connected component and then do the steps recursively.
Okay, but so what is the inductive hypothesis? So these things have Eulerian trails, right?
Yes, ma'am.
Each of these. And you're trying to do a cut and paste? Is that what you're trying to do?
Yes, ma'am. So while taking the original cycle, instead of going in a loop, at the point where you have a connected component,
Walk inside that.
yes.
Right. So that's exactly what we should do. So we know that every vertex has even degree, even in H, because we did not like add any edges, we only removed. And for every vertex, you have removed 2 edges, right? So you have removed a cycle. So which means at this point, you remove 2 edges, this and this. So the degree dropped by 2, so the degree still remains given. And in each of these components, you know that there are Eulerian traces. This, so let's say this one would be probably something like this. And this, so now you have to just cut and paste. So you look at the cycle, if the vertices are C1, C2, C3, C4. At C1, if there is a connected component, then paste the Eulerian trail there. Let's call this P1. You come back to C1, now move to C2. There might be an Eulerian trail there. If there is a connected component hanging around, use the trail P2. Maybe there is no connected component, then you directly move to C3. So this way you can construct an Eulerian trail for the entire graph. So use Eulerian trails for connected components to get Eulerian trail for G. In this and the cycle. Is the argument clear? If there are any questions, then we can pause and answer. Any questions? No questions? I hope it's clear.
I had a question, ma'am. How did we assume that the various components of each are Eulerian?
So if you look at each of these components, it has edges that are lesser than the number of edges in G, right? Because if you look at any of these connected components, the entire graph, you removed a cycle. So you definitely removed some edges. So the remaining graph certainly has fewer edges than the number of edges in G, and the induction is on the number of edges. Okay, so now the question is, so the question is asking is, so far, what did we think about induction? You assume for n and you prove for n plus 1, right? But I think this is his question. The number of edges in this connected component may be far less than n, right? So for example, this might be like n minus 5 edges, right? That is also possible. In that case, how does induction work, right? Is that the question?
Yes, ma'am.
Yeah. So this kind of an induction proof is called a strong induction. So when we say we are doing a strong induction on the number of edges, we assume that for all n, right, strictly less than n, the statement holds, and we try to prove for n. So the base case is n equal to 1. The inductive hypothesis is for all less than n, this statement holds. For all m less than n, the statement holds, and you try to prove for m equal to n. So such an proof strategy is called strong induction. That's a very important proof strategy. There are like several statements you can prove using this induction strategy. So this was actually a strong induction on the number of edges. Is his question and answer clear?
Yes, ma'am.
Okay. I mean, to others also. This is very important. So the usual thing is the principle of mathematical induction, and this is the principle of strong induction. Okay. So now, so someone had asked this question, right? What happens if there is no Eulerian trail, but there is an Eulerian path, like the one here? There is a Eulerian path from A to C, but there is no Eulerian trail. So then you're given a graph G. How do we determine whether an Eulerian path exists or not? Can someone try to see, like just looking at this theorem? When can you say that a connected graph has an Eulerian path? Sorry?
Except the starting and ending point, every this vertex should have even degree.
And only these things can have odd degree. Right? Yeah. Because these two, you cannot come back into A. The reason you could not come back into A was because we did not have even degree, which means that A had odd degree. Right? That's exactly what she's also talking about. So let me just write this. If there exists exactly two vertices of odd degree, and one vertex is the initial vertex and the other vertex can be the final vertex. So I have like 5 minutes, so I'll use it to prove this. We'll stop there. Okay. So what is one direction? Suppose the graph is Eulerian. Then there is an Eulerian path, right? I mean, I should not say G is Eulerian. Suppose G has an Eulerian path. So whenever we say G is Eulerian, we mean that there is a closed trail. So otherwise, we'll say that G has an Eulerian path. Suppose G has an Eulerian path, which is from one vertex A to the other vertex B. So then, similar to this argument here, right? The path will contribute 1 to the degree of A, 1 to the degree of B, because it starts at A and ends at B. And everything in between will have degree 2 to each. And this A and B can appear like any number of times. So the degree of A and B will be odd, but everything else will be. Is that clear? So 1 to degree of A in the first case. After that, whenever A is visited, it will get degree 2. So then the total degree of A will be odd. Similarly, at the end, degree of B will be 1. And everywhere else in between, the degree contribution will be 2. So totally the degree will be odd. So you have A, you have B1, B2, B3. B. Some of these could also be A. Let's say BK, that can also be B. So here, the degree will be 2, degree will be 1. Here it will be 2, here it will be 2, here it will be 1. And because every edge occurs exactly once in this list, we know that every vertex except A and B has degree 2 and A and B have odd degree. I mean, every vertex except A and B has even degree and A and B have odd degree. Is it clear? Okay, so the other direction, suppose you have two vertices of even degree and A, B are the ones. I mean, sorry, odd degree. Sorry. This instead. So what does it mean? You have A here and B here. Let's say this has degree 1. And B has, let's say, degree 3. So now what should you do? What do you think you should do?
Ma'am, if A and B are connected, you remove the path between A and B, and if they are not connected, you add the path.
If they are not connected?
If they are not connected, I mean, if there is no edge between A and B, you add an edge, and if there is not an edge, if there's already an edge, you remove the edge.
Okay, so what he's saying is actually right. So if AB is not an edge, just add an edge. Now, as soon as you add an edge, what happens?
Both of them will have an even degree.
Right, so degree of A is equal to degree of A, degree of B is equal to even. And you already know that every other vertex has even degree. So now you get that all vertices have even degree. So what do you know?
There is an Eulerian trail from A to A that includes the AB path.
Correct. So there is an Eulerian trail from A to A, right? I will just write Eulerian trail. Right? So it begins somewhere here, maybe even here. It will visit everything and then come back correctly. Right? So now you use that Eulerian trail and just remove the edge AB from the trail. AB appears exactly once in the trail, right? Because every edge is visited only once, and that trail, that path will be an Eulerian path. So there is an Eulerian trail P. P, and consider T minus the edge AB. That will be an Eulerian. We are just trying to make the graph have even degree for every vertex, and then consider the Eulerian trail and remove this edge. And you get an Eulerian path. Is that okay? Right. So for an Eulerian trail to exist, all the vertices must have even degree. For an Eulerian path to exist from one vertex to another vertex, you have to first identify if there are exactly two vertices of odd degree. Then you can only limit your search to those two vertices. For example, if I give you a large graph, right, instead of this one, and ask you whether the graph is has an Eulerian path or not, you know that there are only two odd vertices. So you know that if there are exactly two odd vertices, definitely there is one. And this must be the initial vertex and this is the final vertex, or vice versa. So only these you will have to sit and enumerate. Okay. So these are characterizations for Eulerian trails in undirected graphs. So now I'm going to leave with the question. Can you come up with the statement that is analogous to theorem, to this theorem, this Euler's theorem, for digraphs? So connected digraph is Eulerian if and only if when I say Eulerian, it has a closed Eulerian trail. This is one. Okay, so I will just leave with one question. So this whole story was about understanding whether you can identify walks or trails on graphs where every edge occurs exactly once, but you can repeat vertices. Right? Like you can enter via this vertex, come in via this vertex, and do everything. But on an edge, you have to walk only once. So, what is a complementary notion of this? Like what would you expect?
Ma'am, for any vertex, the in degree will be equal to the out degree.
So you are trying to figure out this condition?
Yes, ma'am.
Yes, this is correct. So let's see how many of you can prove it. It's an exercise, so I'm not going to prove this in class, but this is the solution. Yeah, that's right. You got it right. Because you will enter via 1 and leave via the other, right? So you have to get the 10 degrees equal to. Yeah, but I think I broke the suspense for this. I hope it's fine. Okay, so the question that I asked after this, right? What do you think is a complementary notion to that of Eulerian paths? Also, can you go over this graph where you visit every vertex exactly once, right? Instead of the edge exactly once condition. Right? You have to so you can think about this like you have cities and there is this traveling person, salesperson who is going to each city and is going to sell items. Then he wouldn't want to visit the same city again and again, right? On his way back. So he should know which cities he has already visited. So the question is, you start at one city, visit every other city and come back to the same city, but you visit every city exactly once. Right? So this was also studied. This problem is called the traveling salesperson problem. It's a very famous problem in computer science. We'll see some graph theoretic adaptation of this in the next lecture. So probably stop. Yeah, if there are questions, then you can ask. I'll just stop the recording.